First order of business is to see if there's any questions left over from yesterday. Everyone's comfortable with quantum gates, the idea of quantum gates? Okay. I guess then I wanted to start by making a point that came up actually in one of the questions after lecture yesterday, but I think is a good one to advertise to everybody because it kind of emphasizes the difference between quantum gates and classical gates in a way that's a little bit surprising. So in particular, if you think of the C0 gate, so remember what this does. It's a classical gate, but you can apply it on qubits. It takes 2 input qubits and gives you the XOR in the second register. So, I mean, if you think of this as a classical gate, the control bit is just kind of a bystander here, right? It doesn't change. And the target qubit, the second qubit, does change. But actually, in the quantum case, that's not really true. There is no such thing as a bystander qubit in a gate. I mean, except one that's not involved at all. One way to see that is to imagine applying the C0 gate to the following input state, 0 plus 1. Here. Tensor 0 minus 1. Okay, so let's calculate what happens if you do this. Well, we can expand this as 0, 0 plus 1, 0 minus 0, 1 minus 1, 1. Okay, and then we do C0 on each of these terms, keeping the same sign. And so we get 0, 0 plus 1, 1 minus 0, 1 minus 1, 0. And now we can reorganize this by capturing the 0 here. So we get a 0 times 0 minus 1, and then plus 1 times 1 minus 0, okay, which can again be written as 0 minus 1, because we have 0 minus 1 here and 1 minus 0 here, tensor 0 minus 1. Okay? So completely straightforward calculation, but what you get out of this is you see that when we apply the C0 to this pair of states, the plus minus state, it's the target qubit that stays the same, and the control qubit that gets changed to something orthogonal. Okay? So this can be codified. There's actually a circuit identity, which is, if you look at the C0 gate, it's equal to this circuit, where you do Hadamard's, and then you do a C0 in the opposite direction, and then you do Hadamard's again. Okay, so the direction of the C0, whether it's from first qubit to second qubit or from second qubit to first qubit, is kind of a subjective thing. It depends on what basis you're looking at. Okay, so it's one thing for me to say just airily, oh, we can take these classical gates and turn them into quantum gates by putting kets around everything, and that's true to an extent. But actually, including the superpositions, in some sense, really changes the behavior. You can get a lot of very different behavior out of quantum gates that you can't get out of classical gates just because of the existence of superpositions, even when the gates themselves are kind of ultimately classical gates. Okay? Okay, so then the next order of business is to talk about universal gate sets. So yesterday we talked about some examples of fundamental gates, but really we'd like to be able to do an arbitrary operation, right? And this is something we can talk about either classically or quantumly. And the question is, can we build these arbitrary operations out of the small sets of gates that I've given you? So let's start by thinking classically. So for universal classical gate sets, what do we want to do? Well, an arbitrary function is what we can calculate. So we have some inputs x1 through xn, and we calculate f of x1 through xn, right? And so in the irreversible case, we don't need to keep the inputs. In the reversible case, we might need to keep the inputs, but we can always make it reversible by having the output x1 through xn and then f of x1 through xn, right? As you should remember from yesterday. So what gates do we need to be able to calculate an arbitrary function? Well, I don't want to go through a completely detailed proof, but the basic observation is that OK, so these things are bits, right? x1 through xn are bits, and there's n of them. So there's only kind of finitely many inputs that we can deal with. It turns out that that any function at all, given that there's only finitely many inputs, can be written as a polynomial. Okay? In the worst case, you could imagine, well, let's take every point and interpolate a polynomial through them. But actually, we don't. Well, yeah, OK. So that's sort of what we end up doing. But there's a further observation. OK, so let me write that. Which is that since we're dealing with bits, squaring one of the inputs doesn't really matter, right? Because if you square a bit, 1 squared equals 1, 0 squared equals 0. So x squared equals x for bits. So really, the only things that appear in the polynomials are products, right? And the terms are just a question of which products. I mean, so the polynomial is just a question of which products appear, and we're just summing them up. We don't even have any coefficients because multiplying by 2 also doesn't make sense for bits. And minus 1 is equal to 1. So the maximum degree we can possibly have is the product x1 through xn, so that's degree n. Now, the degree thing doesn't really matter for the question of universality. But it's an observation that kind of gets you thinking in the right direction. So the point is we need to be able to have sums of these input variables and products of these input variables. And then we can put them together and get an arbitrary polynomial, and therefore an arbitrary function. Okay? So if we're talking about irreversible gates, it turns out that there's a couple of different possible universal gate sets you can have. But one simple one is not an and. Okay? So these are both gates I showed you yesterday. And, remember, basically takes the product of two variables, a and b. Well, in this terminology, you can think of it as adding 1, mod 2, right? Because 0 then becomes 1, and 1 becomes 0. And it turns out that by combining not and you can also make the or. And you can make the XOR and other things like that. So the and is giving you the products, and the XOR basically is giving you the sums. Then between them, you can put them together into an arbitrary polynomial. Yeah. Yeah, so that's right. So there is a single. Since I didn't talk about the NAND gate yesterday, I decided not to do it. But there is a single gate, irreversible gate, which basically combines not and that lets you be universal with just one classical gate. Yeah.
Can you explain again why we only can have polynomial functions?
Yeah. So the easiest way to think about it is, given any set of points, any finite set of points, you can always interpolate a polynomial through them. Okay. Yeah. And there's only finitely many possible inputs here. So there you go. That's an easy way to show it. Now that would tell you that maybe it's a polynomial of degree 2 to the n. Okay, but that further argument shows that doesn't happen. So anyway, so not an AND is a universal classical gate set for irreversible computation, which means that putting them together, you can calculate any function. And but then if we go to reversible gate sets, well, we don't have the AND anymore. So presumably, the natural thing to do is to include the Toffoli gate. And I mean, we could throw in the NOT gate, but actually what's convenient is to instead include something kind of simpler that you're almost likely to do anyway, which is 0 and 1 ancilla states. So classically, maybe this is not something that people think about, but in the quantum context, it makes maybe a little more sense because there's more interesting single qubit states. The point is that if you take the Toffoli gate and you put a 0 in the third register, then you're calculating the AND of the first 2 bits. Right? That was kind of how we introduced it. So we get the AND gate out of this combination. And moreover, if you take the Toffoli gate and you put a 1 in the first 2 registers, then it does the NOT on the third register. So the Toffoli gate kind of combines both of these 2 gates. But the catch is that to do this, you're going to a 3-bit gate, rather than here we had 2-bit gates. Obviously, you can't be universal with just 1-bit gates, because you can never get any 2-bit operations, right? All the bits will act independently. So that's the way, well, that's kind of the most common universal gate set that people talk about for classical reversible computation. Okay. Let's see, okay. So that's classical computation. Now let's move to quantum universal gate sets. So in the quantum case, our goal is to do an arbitrary unitary transformation. Right? We have n qubit Hilbert space, so it's a 2 to the n dimensional Hilbert space. So we want to do arbitrary elements of SU 2 to the n. So why is it SU 2 to the n rather than U 2 to the n? Well, the global phase has no physical significance, right? So if we get a unitary, but the overall phase is wrong, who cares? It's not going to show up in any kind of measurement we make or any calculation we do, anything like that. Okay, so how do we do this? Well, again, so in this case, the proofs are actually much more complicated than in the classical case. So I'm definitely not going to do them. But there's actually a further distinction that we should make. So one possibility is we could try to get unitaries exactly. Or we could try to get them approximately. Why didn't this distinction show up classically? Well, classically, kind of everything is discrete, right? There's no such thing as an approximate, I mean, there is such a thing as approximately getting the function right, but the only way that could be is if it's actually wrong on some inputs. But maybe it's only a few inputs, right? So that's one sense in which you could say it's approximately correct. But the thing is that if you do that function and you happen to have one of those bad inputs, then you're out of luck. So that's not really a good thing to do if you're really trying to get a universal set of gates. But in the quantum case, that's not really it's not really true, right? Because if you get a unitary, but it's off by just a teeny tiny rotation, right? That's something that's really, really hard to tell. And in fact, you won't be able to tell it. I mean, there's no way to tell it at all unless you do the same calculation many, many, many times. Okay, which I mean, conceivably you could do, but you know, it seems like a lot of work just to see that you did it wrong. I mean, I'm being facetious, but of course there are cases where you want to know about the small differences like that. But anyway, okay. But here's the thing: is that for any given number of times that you want to do it, there's if it's you know, off by some small angle theta, right? And you do it, you know, 1 over theta squared times, something like that. You might see the difference, okay? But if you have the capability of doing it to arbitrary accuracy, then you can figure out, well, how many times am I going to do this gate? Or how many gates am I going to do? And each one of them is off by a little bit. And of course, the errors can add up over the course of the computation. But I'm only going to do so many gates. So if my accuracy is better than that, then I'm not going to have to worry about it. So if we have the capability of approximating gates to arbitrary accuracy, that's really good enough for pretty much any purpose. Sometimes, you know, it's nice just for aesthetic reasons to be able to say you can do it exactly. But in real life, you can never do anything exactly, right? Because, I mean, there could be unitaries that involve uncomputable numbers and all sorts of horrible things that you'd never be able to do in the lab. Yeah?
You need an infinite number of gates to be able to do them exactly, right?
Yes, that's right. Yeah, so... Right, so the argument for that is maybe not completely the obvious one. So this is an uncountable set. Because you can do arbitrarily long circuits, you can still actually do an infinite number of gates exactly, even with a finite number of kind of initial possibilities. But it's only a countable set. So in order to actually get all of the, you know, the real numbers that appear in these amplitudes, you do need an infinite set to start with. To get it to arbitrary accuracy, we don't need that, because all we need to do is we need to get a dense set of gates. And you know, even an uncountable set like SU2 to the n can have a dense countable set, right? Like the real numbers is an uncountable set, but the rational numbers is a countable set, is dense. In the real numbers, you can approximate any real number by a rational number. So kind of the gates that we get out of here are kind of the maybe some quantum version of the rational numbers. That's just a vague analogy. Don't do anything with that except give it as an inspiration. Okay, so what are some universal gate sets? So for exact synthesis of gates, I mean, there's multiple different universal gate sets that people usually use, but a very common one that people think about for exact universal gate sets is the C0 plus arbitrary single qubit unitaries, all single qubit unitaries. Okay? And again, it's not totally obvious that this works, but, well, okay, it's obvious that you can get arbitrary single qubit unitaries this way. But with a little work, you can get arbitrary 2-qubit unitaries and multiple qubit unitaries. Oh, yeah, it's maybe worth saying that my assumption when I'm talking about these things is that we can do the C0. When I say we can do the C0 in this universal gate set, I mean we can do it between arbitrary pairs of qubits. Okay, you can look at kind of a more restricted set of rules where you say, oh, I can do C0s from 1 to 2 and from 2 to 3, but maybe not from 1 to 3 because they're not next to each other, something like that. And you can talk about universal sets of gates in that kind of context as well. But for this case, we're not going to make any restrictions like that. Okay, so this is the most common one, but again, you can think of other universal gate sets. But then talking about approximate gate sets, well, again, there's multiple ones that people talk about. So let me write down 2. So in terms of the gates I introduced yesterday, one of them is the Hadamard, the the r pi over 2, which is this pi over 4 phase rotation. So this has the Hadamard. You will get a lot of practice with, I think, over the next couple of weeks. This one is a diagonal gate 1i, and then of course the C naught. Oh, sorry, this set uses a Toffoli gate. Doesn't need the C naught because this Toffoli gate kind of includes the C naught. Again, because we're kind of imagining ancilla creation there. Yeah.
How can we get arbitrary rotation?
Well, you don't get arbitrary rotations. Remember, this is approximate synthesis. But so these two things don't commute. Okay. So by doing a sequence of these two gates. Oh, sorry. This is more complicated. Let me talk about the other set first. And this is a little harder to show this universal. Yeah. So in this case, you have to kind of add extra qubits. I mean, you have to, because the Toffoli gate is on 3 qubits. Using 3 qubits, you can kind of, so suppose you want to use arbitrary single qubit rotation. Nevertheless, you'll still have to use the Toffoli gate. So you're gonna have 3 qubits. 2 of them are going to be basically ancillas, bystanders. I mean, they could actually be in an arbitrary state. But by doing an appropriate sequence of things, you can kind of get back to something that's almost a single qubit gate that has a weird angle. Now, this other one, it's maybe a little easier to see, although it's still not easy, which is the pi over 8 phase rotation. So that's the square root of this thing. And the C naught. Yeah, well, it's most commonly said the pi over 8. But using the notation I used yesterday, the subscript here, the theta, is pi over 4. So this is diagonal gate 1 e to the I pi over 4. But you can also write that, remember, as e to the minus pi over 8, e to the plus pi over 8. So anyway, I mean, it's true that what I said, that these two things don't commute, and then by taking different products of them, you can get other gates. But the thing is that these two things, they also don't commute. When you take products of these, you eventually run out of possibilities. That you only get a finite set of gates by taking products here. Taking products of these, you don't. You can get an infinite set of gates. And in fact, they're going to be dense in the single qubit unitaries. And so then, of course, once you get dense in the single qubit unitaries, then you're very close to this set. And so you can see how that extends to a universal approximate set of gates. Okay? Okay, so one thing to emphasize about these universal gate sets is it's just saying that it is possible to get an arbitrary unitary or an arbitrary function. It's not saying it's efficient to do that. It might take a really long time. And in fact, just by counting the number of functions, you can see that there are going to be some functions that require an exponential number of gates in n, the number of bits here. An exponential number of gates to actually implement them. And similarly, to get within a fixed accuracy epsilon of some arbitrary n qubit unitary requires, in general, exponentially many gates as a function of n. Okay, so once n starts to get reasonably large, 10 qubits or something, that can be an awful lot of gates. So what we'll do next week is when we talk about algorithms complexity, is we'll examine special cases where we know how to do it in much less than that. Where we can get big improvements over this worst case and actually figure out good circuits to come up with something. And in general, the study of algorithms complexity is basically confronting this problem head on. What functions can we find efficient circuits for, and what are those circuits? Okay. Okay, so this was all I wanted to say about universal gate sets. So are there any questions on that? Yeah.
Why is circuit complexity a good model for the complexity of a quantum computer?
Okay, so this is I guess it depends on exactly what you're asking. I mean, so there's many different models of computation that people talk about. As I think I'll discuss briefly next week, they're all kind of equivalent in terms of the answers that they give you as for whether something is efficient or inefficient. Although there is apparently a difference between quantum and classical. But that's, the fact that there is that difference is already a big deal. So as to why people like to use the circuit model specifically, I mean, people have dealt with other models. The circuit model is nice because it kind of breaks down the computation into a sequence of very simple steps that you can imagine implementing in an experiment. In reality, of course, in the experiments, they don't have a button that says Hadamard gate. It depends on the implementation, but they might have to do a sequence of things to implement that Hadamard gate or the C0 gate or whatever. So the fundamental things for any particular implementation might be different than this. But it's useful to have a common language that kind of everyone can communicate with. If you go to some alternate model of quantum computation, like quantum Turing machine, that's kind of less close to the physical reality. It involves some tape of qubits and some head that moves around, and people don't build computers that way. So this is a little bit closer to the implementation while still being abstract enough to be a kind of a universal common language. Okay? Other questions? Okay. So then let me move on. So the next topic I wanted to discuss is the no cloning theorem. So I guess that you've probably seen this before, a lot of you, but I just wanted to go through it quickly. And in particular, I wanted to go through it because it was at the root of some of the questions that I was getting yesterday. So the no cloning theorem says that there is no quantum device. And now I'm not restricting just to unitary maps. I'm also talking arbitrary, completely positive trace-preserving maps, general superoperators. So there doesn't exist any quantum operation that takes some arbitrary state psi and maps it to two copies of psi. Okay? And the proof of this is very easy. So imagine we have some operation which does this. So proof by contradiction. And so we have two states, phi and psi. So phi should go to two copies of phi. Psi should go to two copies of psi. Now, by anything you do in quantum mechanics is going to be linear. So by that linearity property, the state phi plus psi should go to the sum of these. Phi phi plus psi psi. But if you compare this with what the cloning map would want to give you, well, that's phi plus psi tensor phi plus psi, which, if you expand it, is phi phi plus psi psi plus cross terms, psi phi and phi psi, which don't appear up here. And those cross terms are non-trivial. I mean, there's no way to get them to cancel out unless maybe phi and psi are the same, or opposite, something like that. So this just shows it doesn't work. It's that simple. Okay, so this is something that is kind of one of these fundamental properties of quantum information that distinguishes it from classical information. Classical information you can always copy. Quantum information you can't. But and this is where the relevance to the questions from yesterday comes up. But there's nothing that prevents you from copying certain quantum states. It's just there's no machine that copies arbitrary quantum states. So in general, you can't copy, in fact, non-orthogonal states. I think that may have been one of your tutorials. But copying orthogonal states, that's OK. And in fact, the CNOT does that, right? So suppose you have a qubit here, which could be either 0 or 1, right? And we have another qubit here. We stick in an ancilla 0, and we do the CNOT. Then the output here is either 0, 0, or it's 1, 1, right? And that's fine. I mean, I've explicitly shown you how to make this copying machine. But it only copies these basis states. Let's see what happens if we put in something that's not a basis state. So if we put in, instead, alpha 0 plus beta 1, OK, what do we get on the output? Well, we get, so the 0 term becomes 0, 0. The 1 term becomes 1, 1. So we get alpha 0, 0 plus beta 1, 1, which is an entangled state. It's not the tensor product of two copies of this thing. So that's kind of the general phenomenon here, is that it's perfectly fine to copy in a single basis, but then when we try to extend to superposition states, we get entangled states out of this copying. OK? OK. So any questions on the no-cloning theorem? OK. So so the next topic is, again, something that I think you did in a tutorial, which is quantum teleportation. So now that we have these quantum circuit things, it's maybe nice to see an example of a particular quantum protocol that's actually, interesting for other reasons than just being an example of quantum circuits. So quantum teleportation is a kind of a communications protocol. At least that's how it's normally phrased, although you don't have to do it that way. So we have Alice, and we have Bob. And Alice has some qubit that she wants to send to Bob. OK? Now, the catch is that, so if Alice and Bob have some quantum communications channel, so Alice has some optical fiber that preserves coherence, she can send psi as photons to Bob, and then Bob gets psi, and everybody's happy. But the catch in the case of quantum teleportation is that Alice and Bob don't have a quantum communications channel. All they have is a classical communications channel. So Alice can send classical bits to Bob, but not quantum bits. And so one thing you might imagine doing is Alice could say, oh, well, I'll take this quantum state and I'll measure it, and I'll find out what it is, and then I'll send that information to Bob. Of course, that doesn't work, because any measurements that Alice makes will lose some information about psi. She can't ever exactly learn what psi is out of any set of measurements. So that's kind of hopeless. But it turns out that in the case where Alice and Bob were together in the past, and in the past they established a shared entangled state. So this state is going to be 0, 0 plus 1, 1. And each one of them has one of these qubits. OK? So one qubit here, you see, is held by Alice, and one qubit is held by Bob. OK? Now there's something they can do. That something is quantum teleportation. And so the way that works is Alice has 2 qubits, and so she's going to make a Bell measurement on them. So a Bell measurement we can implement in the following way. We do a CNOT and then a Hadamard, and then we measure these 2 qubits. OK? And so Alice gets 2 classical bits out of these measurements. And she sends them to Bob. And then Bob based on those 4 possible outcomes you could get this way, right? 2 classical bits. And so he'll do one of the 4 polys, depending on which outcome it is. And then based on that, he gets back the original state psi, exactly. So the polys here, of course, are the identity x, this is a bit flip. Y is kind of combined bit and phase flip. And then z is just the phase flip. OK? Like I said, I think you did this in a tutorial, but I wanted to remind you of it because it's kind of one of the simplest but still most interesting and useful quantum information protocols. So maybe it's worth saying why it's simple. And well, simple is obvious, but the interesting and useful part. So it has kind of a number of applications from a quantum information perspective. So the first one is, well, the obvious one that's given the description that I said, which is that we have people communicating qubits, or we imagine we want to do that in the future. But maybe quantum networks are not fully developed. So they can simplify the problem by breaking it up into kind of a classical communication task and a quantum thing that can be done ahead of time, which is preparing these entangled states. Okay? And there's definite circumstances where that's easier than just sending the qubit directly and hoping that it has, that it gets there all right. So that's one application. It's also kind of useful if you're building a quantum computer, because if you imagine having a big quantum computer, you might have some qubits over here, some qubits over here, and it's kind of hard to get them to talk to each other because they're far apart. Well, quantum teleportation, again, can be useful for this quantum communication task of moving qubits around in a quantum computer. So in that case, Alice and Bob are just different parts of the same computer. And actually, there's even more applications for quantum teleportation that don't involve communication. It's kind of a useful building block for all sorts of quantum protocols. I mean, by changing what this entangled state is, you can use it as a nice way of doing implementing certain kinds of quantum gates, for instance. Again, breaking them down into kind of potentially easier tasks. From a theoretical point of view, you can sometimes analyze protocols by thinking about quantum teleportation as maybe as an intermediate thing, because it's such a simple building block. Yeah.
It's also like the information about psi is kind of not kept in the 2 classical bits or in like Bob's state.
That's right. Yeah. So right. So yeah. So from a purely classical perspective, this is either very trivial or very mysterious. So it's trivial in the sense that, well, sure, we're sending information from Alice to Bob. Why is it strange that we can send a qubit from Alice to Bob? But when you start to think about some of the basic properties of quantum mechanics, again, there's no measurement that Alice can do that will actually find out everything about psi. And it turns out that if the measurement she does actually does learn anything about psi, that this won't work. Right? Because by learning something about psi, she disturbs it. So what she actually wants to do is do something that measures nothing really about psi itself, but only about its relationship to this entangled state. And so the classical bits by themselves then have no information. But when you combine them with the entangled state, obviously, then you can exactly reconstruct the state. Yeah, maybe it's also worth mentioning the connection with the no-cloning theorem. I mean, if you think of a Star Trek-style transporter, where supposedly some device scans everything about the person and then sends the information, someone makes a copy of them. Normally in Star Trek there's only one copy at a time, but occasionally there would be some episode where there's a transporter copy and you get 2 copies. In the quantum case, that can never happen, right? Because of the no-cloning theorem, we know there's no way to do that. I mean, I said there's no way to make an exact copy of the state, but there's also no way to make an evil twin of the state. Because this measurement here is destroying the state that Alice had, we're only getting this one copy out at the end. Okay? So, it all hangs together, which it should. Yeah.
You said this was easier than just sending a qubit. What do you?
Well, in some circumstances, yeah. So so I said at the beginning, imagine if Alice and Bob have some optical fiber that preserves coherence, then she can just send photons through that, and Bob will get them at the end. But suppose it doesn't preserve coherence perfectly. It does a pretty good job, but not perfectly. Okay. Well, later on in the course, we'll talk about quantum error correcting codes that allow you to correct for that sort of thing. But actually, what turns out to be easier usually, okay, so the most common thing that happens is sometimes the photon will get lost along the way. Okay, so instead of if Alice sends her qubit through this channel, and it happens to get lost along the way, then they're out of luck, right? It's gone. But if what they do first is they try to create an entangled state, okay? So Alice sends, okay, I'll create an entangled state and I'll send one photon through the fiber. And then Bob at the other end can say, yes, I got the photon. Everything's okay. Now please teleport your state. So the state here, which we're trying to preserve, is never exposed to the noise in the channel. It's only the entangled state which is expendable. And like I said, there are error-correcting codes that can correct for loss in the channel, but it's actually easier to correct these EPR pairs because you know what they're supposed to be and you don't really care what happens to them. Yeah?
In this case, you just mentioned that the state which is sent to Bob gets some kind of noise in the channel.
Right.
Does that affect significantly then the teleportation of the state?
Yeah. So if the EPR pair is not perfect, then it has some small errors in it, but it's close to perfect. Then the state that comes out won't be perfect. It won't be exactly psi either. It'll also have some errors in it. So if you want to do this in real life, you should make every effort to make your EPR pair as good as possible. Of course, if there's errors in the other part, if the spell measurement is not perfect, that can also cause errors and things like that. So the reality is it won't be perfect, but there's not kind of any catastrophic failure, right? If it's close to perfect, if everything is close to perfect, then the output will also be close to perfect. Yeah.
Is this the basis for quantum cryptography as well?
Not exactly. It's not. It's related, and actually, quantum teleportation is kind of one way you can prove this. It's a component in one of the security proofs for quantum cryptography. But quantum cryptography, I mean, one version of it uses entangled states. One version of it doesn't use entangled states. Maybe what you're thinking of is this business I said about sending the photons on first, sending the entangled pairs on first. Yeah. So that sort of thing is the basis of what's called a quantum repeater. So if you want to do quantum cryptography over long distances, then you really have this problem that you're sending very long optical fiber. The chances of getting lost along the way are very high. So you really don't want to send anything that you care about directly through this thing. Instead, you want to set up this quantum repeater in order to send it further. This sort of thing I will talk about in the last week in much more detail, including quantum cryptography. Okay. So, any other questions on quantum teleportation? Okay. So the next thing I want to talk about. Well, I feel bad leaving this big blank blackboard, but let's start a new topic over here. The next thing I want to talk about is actually a bit of a segue on one of those last questions. So I said, if the state is close to perfect, then if the EPR state is close to perfect, then the output state will be close to perfect as well. So what does it mean to say that the state is close to perfect? And in general, how can we talk about the distance between two different quantum states? So this is actually a surprisingly subtle question. There's not really a unique answer to it. Instead, there's kind of two good answers that are the most common things that people use. And so those answers are the fidelity and the trace distance. So let me first talk about the fidelity. So the fidelity for two pure states is kind of the obvious thing, the first thing that you probably think about, which is it's basically the inner product. So if we have two pure states, psi and phi, then the fidelity between psi and phi is the absolute value of the inner product. Okay. Why the absolute value? Well, the inner product certainly is some notion of how similar two states are, but it can be complex, it can be negative. So in order to make it a kind of a nice real number, we take the absolute value. Yeah? You can do that. That's an alternative definition that sometimes gets used. This, I think, is more common. Yeah, I mean, they're equivalent, obviously. Oops, next page. So for pure states, this is a pretty good thing to do. But what about mixed states? Well, so to see what to do with mixed states, maybe let's think a little bit more about what this really means. So this thing has what's called an operational interpretation. So the operational interpretation is, suppose somebody gives you one of these two states, psi or phi. And you make the measurement. You think that is probably psi, but you want to check that. So to do that, what would you do? Well, you'd make the measurement that's psi and then the orthogonal subspace to psi. Right? So this is kind of the measurement that tells you, is it psi or not psi? And if you do that, but the state is actually, so if you do it and state is psi, then certainly you'll always get this outcome, assuming no errors in the process. But if the state is actually phi, it's still possible to get this outcome. And the probability of doing that the probability of the first outcome is the fidelity squared. Right? That's kind of basically just Born's rule, simplest measurement rule in quantum mechanics. Okay? So this operational interpretation you can start to generalize to the case where we're looking at the distance between a pure state and a mixed state. Suppose we have psi and some mixed state sigma. Well, again, if we think it's probably psi, we can do this measurement. And if it's psi, we'll always get the first outcome. If it's sigma, what's the probability of getting the first outcome? Well, so that should be the square of the fidelity. And that's trace of psi sigma. Okay? So this is kind of pointing us in the right direction. But I can pretty much guarantee that unless you've seen it before, you'll never guess what the definition is for two mixed states, because more complicated. And so here's the standard definition, which is the trace of the square root of rho to the half sigma rho to the half. Okay, so now if you unpack this, it kind of sort of looks the same because, well, there's this square root that's taking care of this square here. And, it's a trace is cyclic, so if we move this rho to the 1/2 in front, it looks like trace of rho sigma, and then rho was replacing the psi. Okay? But actually, those are not valid. The square root is inside the trace. It's not the same as squaring the outside. You can't get rid of it by just squaring both sides. And inside the square root, you can't do the cyclic thing. But nevertheless, this is the right definition. And why is that? Well, I think the easiest way to explain that is to write down all the nice properties that this quantity has. And in particular, one of them will show that this is really the right generalization of these two formulas that I wrote already. Yeah?
Does this have the property that your probability of measuring, I guess you don't have RX, you don't have PVM anymore. But like,
Right, so you don't have this simple thing that immediately tells you,
Right.
do we have rho or not? But you'll see that it does relate to that. Okay. So what are these nice properties of fidelity? Okay, well, the first one is maybe the simplest one, which is that it's always between 0 and 1. Yeah, I guess even that is not immediately obvious from the definition. So the second one tells us that if the two states are the same, then the fidelity between them is 1. So that's the same, remember, as in the pure state case, where if the inner product is 1, the two states are the same. But actually, this also goes the other way, also like in the pure state case. So if the fidelity of two mixed states is 1, then that means that the states are the same. And then on the other end, when the fidelity is 0, so that's true if and only if rho and sigma have support on orthogonal subspaces. Okay. So this is the case where they're completely distinguishable, right? Where they're basically orthogonal states. I mean, rho and sigma could be mixtures of lots of different states, but you can think of them completely separately. There's some in the operational sense, there's some measurement that completely distinguishes them, right? You measure the one subspace that has rho and the other subspace that has sigma. Okay, let's see what else. Well, here's something which is a kind of a basic property, but it's not at all obvious from that definition, which is that the fidelity of rho and sigma is the same as fidelity in sigma and rho. Right? The definition up there, that is not manifest, but it's true. Okay, now we're starting to get to kind of the more interesting properties. So the next one is that this fidelity is unitarily invariant. So what does that mean? That means that if you take rho and sigma and you apply some unitary, so you have u rho u dagger and u sigma u dagger, it doesn't change the distance between them. Okay? And that's an important property because, remember, unitary, well, we can think of it as a physical, I mean, in some cases it can be a physical operation, but it can also just be a change of basis, right? So it's a different perspective on the same states. And if fidelity is supposed to be some measure of how close they are, it should be an invariant measure, not really depend on our perspective. Okay, so we like this. On the other hand, if we're doing some completely positive maps on rho and sigma, well, that's not just a change of basis, and in some cases we can actually lose some information, right? So if we lose information about rho and sigma, then they become harder to distinguish. And that means they're closer together, so the fidelity should get higher, because the fidelity equals 1 cases when they're the same. So if fidelity of E of rho, E of sigma is greater than or equal to fidelity of rho and sigma for any completely positive trace-preserving map E. Okay? And last one is the most interesting of all. So maybe I will actually give it its own space up here at the top. So this is known as Ullmann's theorem. And Ullmann's theorem says that the fidelity between rho and sigma is equal to the maximum over purifications psi and phi of the fidelity between psi and phi. Okay, so this is directly relating this mixed state fidelity to the pure state fidelity. So what do I mean by the maximum over purifications? Well, so if rho and sigma are on Hilbert space Q, then we can purify using R. And then we insist that the trace, so psi and phi are pure states on Q tensor R. And we insist that the trace over R of psi is equal to rho, and the trace over R of phi is equal to sigma. Okay, so if we take these pure states on this tensor product Hilbert space and discard the extra system, we get back the original states, rho and sigma. Okay, and what this is saying is that if we pick the best possible pair of purifications, then the fidelity between them is equal, between those purifications is equal to the fidelity between the original mixed states. Okay? You can also kind of understand this in terms of this last property down here, which is, well, tracing over a subsystem, discarding a subsystem, that's an example of a completely positive map that loses information. Right? So if you look at arbitrary purifications, in general, the fidelity should go up when we discard that extra subsystem. Okay? And this is saying that for the best possible ones, it doesn't. Okay? So this I would say is the real reason why it's right to think of this mixed state fidelity as the right generalization of the pure state fidelity. Okay, so I guess one last point about the fidelity. Because 1 corresponds to the case where rho is equal to sigma, so that's when the states are the same, and 0 corresponds to the case where they're completely distinguishable, sometimes that's a little bit unintuitive, right? In that you say there's supposed to be some sort of measure of the distance between them, but actually it's a measure of the closeness between them, right? When it's highest, they're closest. So if people want to talk about the distance between states, sometimes they'll talk about the infidelity, which is 1 minus the fidelity. Okay. Oh, wow, already out of time. Okay. So then let me very quickly talk about, I said this was one of the distance measures that people use. So let me quickly talk about the other one, which is the trace distance. So the trace distance is defined as follows. So we usually just define it directly for mixed states. And it's a half of the trace of the absolute value of rho minus sigma. And this is a generalization of something called the classical statistical distance, which is a distance between two classical probability distributions, which is 1/2 the sum over I of the absolute value of Pi minus Qi. Okay. Yeah.
So is that absolute value in the trace?
Yes, the absolute value is inside the trace. That's very important.
Right, so that's like the square root of rho minus sigma, dagger rho minus sigma.
Yeah, sure, that's one way of defining it. The other thing is that rho minus sigma is Hermitian, so it's diagonalizable. So the easiest way to calculate this is just to diagonalize rho minus sigma. You get this set of eigenvalues. So the trace is just going to look at the eigenvalues. You take the absolute value of the eigenvalues. And so this is the sum of the positive eigenvalues minus the sum of the negative eigenvalues. And in particular, in the case where rho and sigma are simultaneously diagonalizable, you immediately see that this thing reduces to this thing, right? Because then the pi's are the eigenvalues of rho and the qi's are the eigenvalues of sigma. Okay, so so this trace distance also has an operational interpretation. And so the operational interpretation is that if you take the maximum value over P over M's, so P over M's, remember, are generalized measurements. So it's not projective measurements anymore. We're doing some arbitrary measurements. Although I guess actually the optimal is some non-rank 1 projective measurement. But we do the optimal measurement. We take rho and sigma, we do the optimal measurement, and we are trying to guess which we have, rho and sigma. And so if we do the best possible of this thing, then we get the classical probability distributions that we get from the outcome distribution when we make this measurement on rho, and the outcome distribution when we make it on sigma. And this quantum trace distance is equal to the maximum over PMs of the classical statistical distance. Statistical distance between those output probability distributions. So what are they? They trace rho EM, and which is some probability distribution, and trace sigma EM. Okay, and this turns out. So if you have a 50-50 chance of having rho or sigma, and you want to guess which one you have, this turns out to be the best possible measurement you can make to figure out which one you have. And the probability of guessing correctly is then 1/2 1 plus the trace distance. Okay? So again, you see if the trace distance is small, the states are very similar, and you have, not much better than random chance of guessing. Whereas if the trace distance is large, then you do have a good chance. Okay? And so similarly, trace distance has a bunch of properties that are similar to the ones for fidelity. In this case, 0 was still between 0 and 1. But in this case, 0 is the case where they're the same. And 1 is the case where they're different. I guess I didn't write down that property. But if rho and sigma have distance 1, then again they have the rho and sigma have orthogonal support. It's symmetric. So the trace distance satisfies the triangle inequality, which makes it an actual distance measure. So if we have some third density matrix eta, then the distance between rho and sigma is less than or equal to the distance between rho and eta plus the distance between eta and sigma. And then, of course, this thing is unitarily invariant. As I said, that's an important property. Rho sigma for all. And it, so before the fidelity increased under CP-TP maps, but because we've switched the direction of close and far, the trace distance decreases. Okay, so I've run over, so let me just stop there. So this trace distance is a very common method of talking about distance between states, as is fidelity. The whole notion of distance between unitaries and distance between completely positive maps is a much more complicated one, which I probably won't have time to talk about in this course. But if you thought it was complicated to have two different measures of distance, then it's much worse when it comes to operations. Anyway, are there questions on this? Yeah.
Does it make sense to ask the question what happens with probability 5 if we perform different unitaries in each state?
There's not a consistent thing that happens. Okay, think about suppose rho and sigma were two pure states. Okay, and suppose to the first one, to rho, you just do the identity. And then to the second one, you do some unitary. Now, obviously, by doing arbitrary unitaries, you could get arbitrary pure states, right? So sometimes it'll come closer, sometimes it'll go further. So there's nothing really consistent. It's just this thing that is telling you that it's invariant under conceptual things, which are change of basis, that has to apply uniformly to everything. Okay? Yeah.
Is it easy to construct the purification that attains that maximum?
Yeah, it's not too hard. Let me see if I can tell you how to do it offhand. Yeah, so I don't know offhand. I think it's not too hard. I mean, it depends what you mean by easy to construct. I mean, there's a mathematical construction which I think is not too complicated. But if you want to write it down, the Hilbert space is already 2 to the n dimensional. So, when you have n qubits, so it can be a pain to actually do numerically. Okay. So I'm going to be away for the next couple of days. So Aggie is going to take over the class. She will be telling you how to build quantum computers, or at least tell you how other people build quantum computers. Now, I should say that there's also a explorations class by David Corey on the same topic. So I think Aggie will be focusing on different areas than him. But if you're really interested in that, you can learn much more about it later on. OK, thanks.